This is AP Calculus, Lesson 1.6 and 1.7. I'm combining these two into one unit because really they go so well together. This is determining limits using algebraic manipulations. And basically, we have talked about how to find limits several different ways. We've talked about direct substitution, we've talked about graphing and tables. And that's what you're going to use here still. You're always going to try to use direct substitution first. If that gives you the indeterminate form, remember sometimes direct substitution will give you 0 over 0 or some form of infinity over infinity, which would be considered indeterminate form. If you get an indeterminate form, then what you do is you're going to simplify that function using algebra. And there are a whole bunch of different ways you could use algebra. You could factor to cancel things out. You could multiply by conjugates and things like that. And I'm going to show you some of those examples as we go through some of these. A lot of times the algebra will make finding limits easier, but sometimes that algebra associated with this can get pretty difficult. So, you know, if you can't figure out how to do it using the algebra, you always have the graph and the table to fall back on if you need to. I just don't suggest that you use that any more than you have to, because that is time consuming and algebra is going to save you a lot of time. So hopefully you have good algebra skills and you're able to do this without much trouble. In the first example here, I've got the limit of x cubed minus 1 over x minus 1 as x approaches 1. So the first thing I'm going to do is just try to do direct substitution, because if that works, if it gives me a nice integer answer or a real number answer, then I can keep that, and that's my limit. So let's try that first. If I plug 1 in, I've got 1 minus 1 is 0 over 1 minus 1 is 0. I've got the indeterminate form. So I'm going to have to do some algebra to simplify this. Well, hopefully you see at the top that is the difference of cubes. X cubed minus 1. X cubed is a cube number and 1 is a cube number. I'm going to review real quick with you how to factor the difference of cubes. Basically what you do is you do 2 sets of parentheses, and hopefully you had this when you took Algebra 2 and this is not new to you. What you're going to do is you're going to take the cube root of the first term, which is x. You're going to take the cube root of the second term, which is 1. And then you have, so that's just a binomial. And then over here, we're going to have a trinomial. To get the first term of my trinomial, I square this first term, so that will be x squared. To get the middle term, I multiply these two terms together. So 1 times x is just 1x. And then to get the last term, I square the last term here. So 1 squared is 1. Then I have to put my signs in. To figure out the signs, I'm going to look at this sign. It was a minus. And then here, if you can remember the phrase, same, different, plus. This one gets the same as the sign you started with. This one gets a different sign than what it started with. This one always gets a plus. So same, different, plus for your signs in your perfect cube factoring problems. And then I've got x minus 1 on the bottom, which works out nice for us because the x minus 1s will cancel. So when those x minus 1s cancel, then I have something simpler. I've got x squared plus x plus 1, and at this point I can then plug 1 in by using direct substitution again. So if I do that, I've got 1 plus 1 plus 1 equals 3. So the limit as x approaches 1 for this one is 3. We did a little cancellation to simplify that function, and then we were able to find the limit. For the second one, if I do direct substitution and I plug in -3, -3 squared is 9, plus -3 is 6, and 6 minus 6 is 0. And then -3 plus 3 is 0. So again, we've got the indeterminate form, 0 over 0. So I'm going to have to do some factoring to solve that. This is a simple trinomial on the top. So hopefully in algebra, you learned how to factor trinomials. The way I explain this to my students is I tell them to look at the last number here. Multiply that last number by the coefficient of the first term. Well, 1 times 6 is 6. So 6 is kind of our magic number. We're going to find factors of 6 that will subtract to give me 1. Factors of 6 that subtract to give me 1. Well, that's 3 and 2. So I know I'm going to use 3 and 2 to get the 1. Now, since this does not have a coefficient in front, it's real easy. I'm just going to put an x and an x. And then I need to use 3 and 2, 3 in one of them, 2 in the other one. And then my signs, if this is a minus, I know my signs here are going to be different. If this is a plus, these signs will be the same, and they will be the same as the middle term. But this is a minus, so they're going to be different. If my signs are going to be different, to determine which one's plus and which one's minus, I look at the middle term. I want the plus to go with the bigger number. Here, the plus goes with the 3. So I have a plus here, a minus here. I bring over the denominator, and I can cancel out the x plus 3, leaving me with x minus 2. And once I've simplified, I can then do direct substitution. So negative 3 minus 2 is negative 5, and that is my limit. So you see how doing a little bit of algebra is going to make this a lot easier and enable you to find your answers pretty quickly. In the next one, the limit as x approaches 1 of x squared minus 1 over x plus 1. I'm going to first do direct substitution. I always try that first. 1 squared minus 1 is 0. 1 plus 1 is 2. So this one is nice. That one, when I plug 1 in, 1 squared minus 1 is 0. And then x plus 1, 1 plus 1 is 2. Well, that works. That's just 0. So just because I can factor here doesn't mean I need to. I don't always have to factor. Now, if that one had said the limit as x approaches 1 of x squared minus 1 over x minus 1, then when I plug in, I would get 0 over 0, which is the indeterminate form, and that would cause me to have to factor. So hopefully you remember, these are difference of squares. If I'm factoring difference of squares, I take the square root of the first term. That goes in the first section of each set of parentheses. I take the square root of the second term. And then my signs are plus and minus. One's positive, one's negative. And why does that work? Well, the middle term here is 0x. So what factors of 1 subtract to give you 0? 1 and 1. So that's why that works. And then we've got x minus 1. So I'm going to cancel those. That leaves me with x plus 1. And then if I plug in the 1, 1 plus 1 is 2, and that would be my limit of that problem. So you're going to factor to get your answers sometimes, anytime you can. Well, if you've had the indeterminate form, you're going to factor to get your answer. If when you do direct substitution you don't get an indeterminate form, then that answer you got is your answer to the entire question. So sometimes they work out that way. Sometimes if you just do direct substitution, you're going to get your answer right off the bat. Next, we need to learn how to do a rationalizing technique by using conjugates. And if you look here, you've got the square root of x plus 1 minus 1 all over x. And we were looking for the limit as x approaches 0 here. So if I plug 0 in, automatically I get 0 on the bottom. So I know it's at least undefined. If I plug 0 up here, I have square root of 1 is 1, 1 minus 1 is 0. So I do end up with the indeterminate form, okay? And if you look at what you've got, anybody know how to factor that? Okay, it is not factorable. So we have to have another technique to be able to do this. And when you have radicals involved in the expression that you're dealing with, radicals can be simplified by conjugates. And hopefully you remember from Algebra 2 and pre-calculus that the conjugate of a radical is taking the radical with the opposite sign and the same number. So you just multiply this when you multiply by the conjugate. It's basically the same thing, that radical plus 1 and then the 1 on the outside, but instead of having a minus, I'm going to have a plus here. And then basic math tells me that if I multiply the top by something, I have to multiply the bottom by the exact same thing. If I don't, I'm changing the value of my expression. But by multiplying the top and the bottom by that conjugate, essentially what I've really done is I've multiplied by 1. because anything over itself is 1. And when you multiply a fraction by 1, you're not changing the value of that fraction, so you're allowed to do that. So if I multiply these two conjugates, I have to FOIL. If I FOIL this, the square root of x plus 1 times the square root of x plus 1, the radical is going to drop out and leave us with x plus 1. The conjugates, when I multiply two conjugates together, my middle term, the 1 times the square root of x plus 1 is the square root of x plus 1. And then the negative 1 times the square root of x plus 1 is a negative square root of x plus 1. And being true to conjugates here, when we multiply by conjugates, the purpose of doing that is to get rid of the radical sign. And when you do this, the middle terms are opposites, so they're going to cancel out. They're going to be gone, which is the purpose of doing this whole thing. And then negative 1 times 1 is a negative 1. This entire thing, multiplying by the conjugate, will enable us to get rid of all the radicals so that we can have a simple number up top, or a simple, in this case, variable up top. Then we have to multiply the bottom. Well, if I do that, x times square root of x plus 1, I'm going to distribute. So x times square root of x plus 1 is x times square root of x plus 1. And then x times 1 is x. And so then, if I look at what I've got left, on the top, 1 minus 1 is 0. So I have an x left on top. If I look at what I've got on the bottom, both of these terms have an x in them. So I'm going to factor out that x. And that leaves me with the square root of x plus 1 plus 1. And then look at what happens with your x's. They cancel out, leaving me with 1 over the square root of x plus 1 plus 1. So if I now do direct substitution and I plug 0 in, on the top I have 1, and on the bottom 0 plus 1 is 1, square root of 1 is 1, plus 1 is 2. So my answer to that is 1/2. So multiplying by the conjugate gets rid of the radicals and allows us to get a simple answer. In this segment, we're going to talk about limits of trig functions, and we're going to still do direct substitution and just simplify the trig functions that we get after we have substituted. So here I'm looking for the limit of sine x over x as x approaches pi. So if I do direct substitution, I end up with sine of pi over pi. All right, at pi, we're here, sine of pi would be 0. So we end up with 0 over pi, which is 0. So no algebraic manipulation needed there. It's direct substitution. And you're going to find that with a lot of trig function, it's going to be direct substitution, unless it's some sort of special case, or you have to, sometimes you have to simplify, like maybe use an identity for trig and simplify something in to get you something that you can work with. In the next one, we've got the limit of tangent of x as x approaches 0. So we're going to do direct substitution. That's just tangent of 0. And we know from Algebra 2 that tangent is sine over cosine. So if we're looking for tangent at 0, we're going to go to 0 on our unit circle. Sine is the y-coordinate, cosine is the x-coordinate. So sine over cosine would be 0 over 1. So tangent of 0 is just 0 there. In the next one, we have the limit of cotangent x as x approaches 0. So if I do direct substitution, I've got cotangent of 0. So we're still at 0. But now we know that cotangent is the inverse of tangent. If tangent is sine over cosine, then cotangent is cosine over sine. So we need the x value over the y value. Well, if you look at that, that is 1 over 0. That is undefined. And it's okay to have, that is not an indeterminate form, okay? Indeterminate form would have been 0 over 0, or infinity over infinity, negative infinity over infinity, maybe an infinity over 0. So this is not an indeterminate form. This is a function that's undefined. This function is undefined at cotangent of 0. So undefined is a perfectly fine answer to have when you're dealing with limits. Okay, and then there are two special limits I need to make sure you're aware of. These are things that you're just going to have to memorize. There's really no way around it. There are proofs of these online if you're really interested in seeing why these things work. That takes a lot of time to show you why though. So I'm not going to show you, and that would honestly complicate things for you at this point, and I don't think that's going to be helpful if I show you all that. I think it's just going to confuse you more than anything. So just memorize these two limits. They show up periodically as we're doing problems, and if you know what the limits are, it saves you a lot of work in the long run. So for your special trig limits, the limit of sine x over x equals 1 as x approaches 0. So if you have sine x over x as x approaches 0, the answer is going to be 1. Now notice over here, we had sine x over x, but x was not approaching 0, it was approaching pi. So that's the difference here. That's why this one wasn't 1. We weren't approaching 0. So it only works if you're approaching 0. Now if you think about that, if you put 0 in, well, sine of 0 is 0, and if we plug 0 in here, we have 0 over 0. So it is an indeterminate form. So there is a way to show why that works, but you need to just memorize it because there's a lot to discussing why that works. And at this point, I think you're going to be better off to just memorize it. The second special trig limit is the limit of 1 minus cosine x over x as x approaches 0 is 0. So notice, with both of your special limits, they're both approaching 0. Okay. For this one, it's sine x over x. For this one, it's 1 minus cosine x over x. So they're very similar in the way they look. They might not be too hard for you to memorize, but go ahead and get those memorized because it will make your life easier. I do want to also point out that if I have something like the limit as x approaches 0 of sine 2x squared over 2x squared, that limit is still 1. Now, you might say, why? That doesn't say x over x. Well, it doesn't have to. Remember, x is the function, it's some function, okay? So it doesn't have to be x in order for that to work. In order for it to work, these two functions have to be the same, okay? So instead of having x here, I have 2x squared and 2x squared. As long as that is the same, this limit still holds true. So that's a place where I've had students get confused before. As long as these are the same, the limit is still going to work. All right, in this segment, I want to talk to you about these special limits and making sure you understand that sometimes you may have to force your equation to be one of these special limits to get it to work. So with this first one, it says the limit of tangent x over x as x approaches 0. Well, if we do direct substitution, we have tangent 0 over 0, and tangent at 0 would be 0 over 1, which is 0. So we have 0 over 0, the indeterminate form. So we know we're going to have to do something else with that one. So if we look at what we've got, well, I know that tangent is the same thing as sine over cosine. So I'm going to rewrite this as the limit as x approaches 0 of sine x over cosine x over x. Now, hopefully you understand from algebra and from just different division of fractions, really, that if you have something over x, that x is understood to be a fraction of x over 1, and then I can rewrite that as sine x over cosine x times 1 over x, okay? And then I'm still trying to find the limit as x approaches 0, but what I can do is I can manipulate this thing to look like what I need it to look like to be able to cancel out or do some limits. So what I want to do is I want to separate this out. I want to put these, if I put them together, okay, if I multiply those two things together, well, wouldn't that be sine x over x cosine x if I multiply by that 1 over x? Okay, so if I've done that, then I could separate these two things out. I still want the limit as x approaches 0. And I'm going to separate these. I'm going to say that's sine x over x times 1 over cosine x. And then we learned when we were doing our properties that this is the same thing as the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. And then we know from our special limit that this is equal to 1. And then we can do direct substitution here. So if I plug 0 in for cosine, cosine at 0 is 1. So that's 1 over 1. So that's 1 times 1, which is 1. So for the first one, the answer is 1. Okay, so we did a little bit of manipulation there to get it to equal what we needed it to so that we could actually find an answer. For the next one, it says the limit of x, as x approaches 0 of sine 4x over x. Well, that looks very familiar. It looks very similar to this, but we know in order for this to work, x and x, those two things have to be exactly the same. Well, I have a 4x here and an x here. So what does the bottom need to be able to make these two things the same? Hopefully you're saying it needs to be multiplied by 4. Okay, and you're right. It does need to be multiplied by 4, but we're not allowed to just multiply the bottom by something. We have to also multiply the top by that same number because we know the only way this thing is going to stay equivalent to what we started with is if we multiply it by 1. Okay, so I'm going to not just multiply the bottom by 4, but I'm going to multiply the top and the bottom by 4, which means we've essentially multiplied by 1, not changing the value of our fraction. So if I multiply by 1, what I end up having here is the limit as x approaches 0 of 4 sine 4x over 4x. And then we learned with scalar multiplication when we did our properties that this 4 could come out to the front. So that's the same thing as 4 times the limit as x approaches 0 of sine 4x over 4x. And now that these two are the same, we have this situation right here. So I have 4 times 1 to give me my answer of 4. So you can rewrite things, you can use your trig identities to change, you're not really changing the value of anything, but you're changing what it looks like so that you have something that you can work with.